Good afternoon, everybody. Welcome to lecture. Today, we're going to talk about conjugation and dienes a little bit later, but we're going to finish up polymerization. And before we get to that, I want to tell you a couple of things before we start. We're going to first do our survey question from last time. So this one asks about an allylic bromination, and it says, which radical is not an intermediate in the allylic bromination of the molecule in the box? So the molecule in the box has two fused six-membered rings and a double bond here at the fusion point. It has several different allylic positions. It's got an allylic position here at the ring juncture, an allylic position there, and an allylic position there. And so to predict all of the radical intermediates, what you need to do is look at all those positions and imagine plucking an H dot off of every one of those allylic positions where there is an H. And that would be here, here, and here. And when you do that, you get a number of different intermediates. Like you can see, for example, the B structure comes from plucking an H dot off of here, off of that position. If you look at the C structure right here, that comes from plucking an H dot off of this spot right there. And then there's a couple that you have to kind of be aware come from resonance structures of allylic radicals that you might produce. So in other words, A, it doesn't look a lot like this structure in the box here, but when you pluck an H dot off of that position, then you get, by resonance, a double bond here and a radical up there. So that's A. So A is a legitimate intermediate in the allylic bromination of this molecule. And then E it's kind of a similar story with E. E doesn't look much like the molecule in the box at first. But if you imagine plucking an H dot off of this allylic position, then by resonance you get a double bond here and the dot goes there. So E is another one that's an actual intermediate. The only one that doesn't fit, that can't come from abstraction of an H dot off of this molecule is D, structure D. D is not an allylic radical. The dot is not in an allylic position. It's just a regular secondary alkyl radical. So this one is not an intermediate. And when I looked at the statistics for this quiz, it looked really good. I mean, almost everybody picked D is the one that didn't fit. So I was really happy about that. I'm not going to show the statistics, but it was really good. So I think the class is getting this concept pretty well, and I'm glad that, you know, it seems to be sinking in. So that is great. Any questions on this survey question? All right, well, let me tell you something else that's important and significant for today. Today is the day that they announced the 2025 Nobel Prize in Chemistry. So if you've been paying attention, it's Nobel Prize week. Monday was physiology and medicine, Tuesday was physics, today is chemistry, and then there's others that'll be announced later. But it's these three individuals here that won it this year. One of them is from actually, I don't remember exactly where they're all from. I know that this guy is from UC Berkeley, Japan, and this guy's from Australia, Melbourne, I think, Australia. Yeah, he's from Kyoto, I think, University. So their prize was for the discovery of metal organic frameworks, MOF for short. So let me scroll down so you can see what that's all about. Development of metal organic framework. So what's a metal organic framework anyway? Let's take a look and read about this prize announcement. These individuals are awarded the Nobel Prize in Chemistry for the development of a new type of molecular architecture. The constructions they created, metal organic frameworks, contain large cavities in which molecules can flow in and out. Researchers have used them to harvest water from desert air, extract pollutants from water, capture carbon dioxide, and store hydrogen. The way that they work is that the metals form like the corners of these structures, and the organic molecules form the struts that kind of hold them together. So they're organometallic materials. And we're going to talk about organometallics later on in this course. When we get a little bit further along, we're going to talk about metal carbon bonds and how those molecules can be useful. But this is an example of that type of chemistry. And they are potentially really useful, have lots of applications. And that's the kind of thing that Nobel Prizes get awarded for, these paradigm shifting kinds of discoveries that cause people to think about chemistry in a whole new way. So congratulations to these individuals for winning the Nobel Prize this year. Any questions about Nobel Prizes? Yeah.
What they won, like 1.2 million?
They win 1.2 million Swedish kroner. which I don't, it's like, I don't know what the conversion rate is, but yeah, it's some kind of, it's about $1 million. I think it's like something like $900,000, depends on the exchange rate, but, and they'll split that. 1/3 of the prize goes to each one of these individuals. My understanding though, is that the money is sort of it's a nice thing to have, but really the prestige is the big thing that these individuals work for. So if you win a Nobel Prize, it's obviously a big, big deal. And yeah, so very exciting stuff. Let's talk about polymers and polymerization. So last time I introduced polymerization and I talked about the first of several polymers that we're going to cover, polyethylene. So last time we talked about how polymerization works with double bonds. It's a radical process where you put an alkene in with some kind of a radical initiator. The radical initiator reacts with an alkene and it makes a dot on one of the carbons, and then that carbon dot attacks another alkene and you get another carbon dot, and essentially the monomer molecules react together and form a long chain. And the way that we represent that is with this nomenclature that describes the smallest repeating unit of the polymer. This is the part that came from an individual ethylene unit, and then it just repeats over and over again n times, where as every n molecule of ethylene gives a chain that's one monomer unit longer. And these n's can get to be very large, hundreds or thousands even. So the molecules are really big and they have different sorts of properties. Polyethylene comes in two different varieties when you're looking at it as a packaging material. There's high density polyethylene, which has a recycling symbol number 2 with the circular arrows around it, and the HDPE symbol below it, which stands for high density polyethylene. This tends to get used in applications where rigid, semi-rigid plastics are useful, like milk jugs or shampoo bottles. Some packaging materials, LDPE is more flexible. It's more suitable for things that need to be stretchy, like plastics, flexible plastic films, for example, grocery bags, that kind of thing. It's good for those kinds of applications. This gets used for grocery bags too, the plastic grocery bags. It's just different properties that you get between the two of them. So that's a couple of different types of polymers. I'm going to go through the other common polymers that you'll see if you look at packaging. Here's another one that's on the chart of recyclable polymers. It's got a double bond with a chlorine on it. This is vinyl chloride is the name of this molecule. And when it gets polymerized, it forms a polymer that's got one chlorine on the smallest repeating unit and 2 carbons. And the polymer notation looks like this, where the brackets go around the repeating unit and the N represents how many times it repeats. So it's very much like polyethylene. It's just in place of one of the H's on polyethylene, there's a chlorine. And this one's called, well, I'll first give you the symbol. It's got a 3 with the arrows. And there's a V below it. This is polyvinyl chloride. Most people know it as PVC. So polyvinyl chloride, PVC, probably the most well-known application is in pipes, so PVC pipes. If you've ever done any plumbing or been to a home improvement store, you probably have seen the the kind of the whitish plastic pipes. Sometimes they're a little bit beige if you're using a different type. They don't have to be white. That's a pigment that's been added. PVC can be clear. PVC by itself is clear, colorless, and can be used as packaging material. But for pipes, it makes good material for doing that sort of application. So this is a real common one. That's number 3. So we've got 2, 3, and 4. Let's talk about a couple others. This monomer has a methyl group on it, in addition to the H's that are present at the other carbons of the alkene. This one's called propylene. And when it polymerizes, it forms a polymer that's got a long carbon chain with alternating carbons having a methyl group on them. And this molecule, because it came from propylene, it's called polypropylene. And it has recycling symbol number 5. And there's a PP below it for polypropylene. This one is really common in food packaging. If you get any kind of food that's like a microwave meal or something like that, it's almost certainly gonna be packaged with a polypropylene like packing material underneath. If it's a tray you put in the microwave and is heated, it's probably polypropylene, because polypropylene is very has good thermal properties. You can heat it up and it doesn't shrink or deform real easily. It tolerates that kind of stuff really well. So polypropylene is a really good one for that sort of application. And let me see if I've got an example of it in here somewhere. Yeah, I brought a disposable yogurt cup here. And if you turn over the bottom, it's got a number 5 on it with the circular arrows, polypropylene. Lots of recyclables that have the number 5. Let's take a look at one more. This one has the standard alkene, but the group that it has on it is actually a benzene ring. It's a phenyl group. And the name of this monomer is called styrene. Styrene is the monomer, and when it's polymerized, it becomes polystyrene, which has this structure. Every other carbon has a phenyl group attached, benzene ring. And this one gets recycling symbol number 6 with the arrows going around it and a PS below it, and that stands for polystyrene. And if that sounds kind of familiar, this is the polymer that styrofoam is made out of. Styrofoam is a brand name for a puffed up version of polystyrene. They take polystyrene and they introduce gas bubbles into it, and it puffs it up. It makes really good insulation. So this gets used in, well, coffee cups that are styrofoam, but also a styrofoam insulation in homes. There's extruded and expanded polystyrene, or a couple of different types of foams that get made from this. It also gets used for a bunch of other applications too. So not just insulation, but it forms really nice clear plastic films. It can, it's pretty kind of brittle, so it doesn't have, you know, properties that are suitable for everything, but it gets used for a lot of things that require clear plastics. Like for example, disposable cutlery. So if you've ever used a clear plastic like dinner plate that was disposable, it's probably polystyrene, most likely. The disposable forks, knives, and spoons are most likely polystyrene. This disposable cup that I have here is a number 6. This is a polystyrene. So like disposable drinking cups, polystyrene very often. You can look at the bottom to see for sure, but it's one of the really popular materials to make these kinds of cups out of. So you might be wondering, what is the significance of the numbering scheme? 6 versus 5 versus 4 versus 3 versus 1. Anybody know what that comes from? What it tells you if it's got a 1 or a 2, besides the polymer that it is? It's set up in ease of recyclability or value. So the lower the value, the lower the number, the easier it is to recycle, the higher the value. So polymer number 1, which we didn't talk about here, but we'll talk about later on in the course. That one is really highly recyclable and has a lot of value. 2, 3, and 4 are also valuable. 5 is less valuable, and 6 is basically so hard to recycle that basically people don't even bother. It's actually it's a waste product, and really the only good solution is to just dispose of it like in a landfill or incineration. It's not really economical to recycle right now, which is, you know, a shame and a problem, but maybe technology will develop to enable us to do a better job with this one. Or maybe we can find a more sustainable polymer to replace this one with. Yeah, do you have a question? Well, it's not impossible to recycle. It's just nobody wants it. You have to pay people to take polystyrene away. So there are ways to recycle it, but you lose money on the deal. And so nobody wants to do that, at least right now with the technologies we have. So it's not impossible. You can depolymerize it, make it go back to its starting material, that reaction, and then repolymerize it into new material. But it's a kind of a messy, expensive process. So do you have a question over there? PET is polymer number 1, yeah. So that's one that it is right at the top of the recyclability chart, but it's a different kind of polymer. It doesn't form from radical polymerization like these, so that's why we're not talking about it right here. But we'll get to it later on in the course. When we start talking about esters towards the end of the course, we'll talk about PETE. That's polyethylene terephthalate. That's what single-use drinking bottles are made out of. And a whole lot of other things like clamshell food packaging gets made out of PET. And it's one of the most recyclable polymers that's out there in terms of like use. So we'll talk about that one later, but its chemistry is really different than these. So it doesn't quite fit in with this chapter. But yeah, it's a really good question. And there's other types of polymers too. These are just the ones that are present in a lot of consumer plastics that could potentially be recycled. But there are really hundreds of different kinds of plastics out there that have different monomers. Some plastics incorporate multiple monomers and get different properties as a result. It's really a really rich field of chemistry, and the material properties that come out of these things is really what the interest is in them. It's like if you change the N value, you change the properties. If you change the monomers, you change the properties. And the properties might make it a better packaging material or a worse packaging material, or better for one application or another. So their properties can be tuned by their chemistry. So that's why they're so popular. And plastics they're everywhere, and they're going to continue to be an important part of modern life. So solving the plastic waste problem is certainly something that we as a society need to work on, because it's a big problem. So, any questions about these synthetic polymers that come from alkenes, like polypropylene? All right, well, that's the end of this chapter on radicals and radical chemistry. Now we're going to move to the next chapter, and we're going to talk about conjugation, dienes, and the Diels-Alder reaction. So that's what's coming up next. So we're going to get to the Diels-Alder reaction a little bit later, towards the end of the chapter. We're going to start out with conjugation. So far what you know about conjugation is what I told you about when we were looking at carbonyl frequencies in IR spectrometer. So if you had a carbonyl that was, like for example, had no conjugation, it had a stretching frequency of about 1710 inverse centimeters. That was sort of normal for a ketone like this. But then if you put a double bond next to it like this one, I mean, they look structurally very similar, but this one's got a double bond. This one all of a sudden starts showing up at a different frequency. This one is like maybe 1685, and this is just kind of a rough estimate. I don't know exactly what the frequency of that carbonyl is, but it's going to be definitely lower than that one. The difference between these two is that this one has a double bond, single bond, double bond pattern. We've learned to recognize that as conjugation. And what we're going to do in this chapter is learn why that matters. What is it about having another double bond nearby that makes it all of a sudden behave differently? The way that the orbitals interact is what we're going to talk about to try to explain this kind of behavior. It's important outside of IR spectroscopy too. This isn't just like something that affects IR frequencies and nothing else. It affects the reactivity and the stability of the molecule in a lot of ways. So conjugation is an important thing to study and understand. So now a definition of what conjugation is, a simple definition of what conjugation is, so that we can have a more formal way to talk about it than just saying double bond, single bond, double bond pattern, because it's more involved than just that. So conjugation. Whenever 3 or more atoms with p orbitals are bonded in a row, and by that I'm going to say adjacent or next to each other. Whenever you have that situation, you're going to have this property called conjugation. Bonded in a row, adjacent, and can overlap. There is conjugation. So conjugation is about the overlapping of p orbitals on adjacent atoms. Let's take a look at an example of that. Here is, and I think what I'm going to do is switch over to this other board because I want to have lots of space to draw some nice big structures. So I'm going to start off with a molecule that has conjugation in it and is a cation. So here's a molecule that has a carbocation carbon, which is on the right here, and next door is a carbon-carbon double bond. This is a molecule that has conjugation, and traditionally the way we would describe it is with a series of Lewis structures. We draw some resonance structures for this molecule. So resonance structures and conjugation are like kind of very closely related concepts. We're describing conjugation in Lewis structures by drawing a series of resonance structures. So the way that you do it for this molecule is you take a pair of electrons out of this pi bond and you just slide them over. And that would give you a new resonance structure that looked like this, where you have a carbon-carbon double bond between the two atoms on the right. And now the carbon on the left has got the positive charge on it. So those are two different resonance structures that are not different molecules. It's not like it's fluctuating between the two. It's like both of them at the same time. And if you wanted to draw one picture that described these two structures like most accurately, it'd be a picture like this, where you draw a molecule where you show the three carbons, and each of the carbon-carbon bonds is kind of like a bond and a half. In other words, these bonds aren't full double bonds and they're not full single bonds. It's not like the molecule has a single bond in one of the spots some of the time and a double bond some of the time. It's like a bond and a half all the time. And the positive charge is shared over the two end carbons. And that's a picture of this molecule. This is the resonance hybrid. Now, let's talk about these things in terms of molecular orbitals to try to get a molecular orbital explanation of this. So if I draw this molecule with a molecular orbital representation, I'm going to show the sigma bonds as lines, but I'm going to show the p orbitals on these atoms. I'm going to draw them in. This is an edge view of the molecule, trying to represent it as a three-dimensional molecule. And I am going to draw the p orbitals in orange here. So one of the things we know about this molecule right here is that every one of these carbons is sp2 hybridized. That one's sp2 hybridized because it's part of a double bond and it's got 3 electron groups. That one's sp2 hybridized because it's got 1, 2, 3 electron groups. And this one's sp2 hybridized because it's got 3 electron groups. So these all have sp2 hybridization, which means they have an unhybridized p orbital, and that's what I'm drawing in orange here. If we were going to try to mimic this picture of the molecule, this Lewis structure, what we would do is we'd say, well, there's a double bond between the left 2 carbons. That's from overlap between these p orbitals. And there's a pair of electrons that overlap in the space here, and that's what gives the pi bond. Then there's a p orbital here that's empty, and there's a plus charge on this carbon because it's an empty p orbital. That's one static picture of the molecule. That emphasizes charge on the right carbon. Well, you could draw an identical picture over here below it that tries to show this picture right here with the molecule and showing the charge on the left carbon. It's going to be a very similar looking picture. It's just we're drawing the overlap between a couple of different p orbitals, and the charge is going to end up on a different atom. So all the atoms still have p orbitals. And in this picture, which mimics that Lewis structure, there's the overlap between the right 2 p orbitals, and there's a pair of electrons that are shared in the overlap between the upper lobe and the lower lobe. I'm just drawing a couple of dots there so we can keep track of them. It's not like they're stuck in any one spot. It's not like these electrons are only up here. They are up here and below here. And these 2 pictures are trying to show where are the electrons in the molecule. And now what I'm going to tell you is it's not like this one and that one, this one some of the time and that one some of the time. You get overlap between all of the orbitals all the time. So really the picture of this molecule is like this, where there's 2 pi electrons, 2 electrons in the overlapping p orbitals that are shared across the 3 atoms. And it isn't like the positive charge is on the left some of the time and on the right some of the time. It's on both carbons at once. And these dots, they're not localized in any one spot. So I'll just erase them and say that you got to imagine there's 2 pi electrons in this system that are spread out over this whole sort of overlapping array of p orbitals. That overlap of the 3 atoms overlapping with their p orbitals, that's what the conjugation is. So I'll put that in words here. Conjugation. In this system, is this overlap there and this overlap there. The 3 p orbitals overlapping. Think of it as kind of like a road that the electrons can travel on. They occupy this space, and they're kind of free to roam through this overlapping p system. And they're spread out. You can think of electrons as being kind of like waves. They aren't necessarily stuck in any one spot. They're kind of smeared out over this area. So, is there a question?
Yeah. So is that why it lowers like the frequency of it, because it stabilizes?
It has a stabilizing effect, and we're going to talk about exactly why it lowers the frequency for a carbonyl when we in probably the next example. So, or a couple of examples. But it's a really good question. It's like, why is it that that a conjugated aldehyde or a conjugated carbonyl of any type is a lower frequency? So we're going to get to that in a couple of examples. Okay, so this is an example with a cation. Let's look at some examples that are not cations but also important. So let's look at a double bond next, or a diene, a molecule that's got two double bonds in it. So here's a molecule that has a double bond, single bond, double bond pattern. This is called 1,3-butadiene. We're going to use this one in lab next week, actually. If you're in the lab, you'll be working with this molecule. This is the Lewis structure of it. If we were going to draw a molecular orbital diagram of it, I would draw that like this. I would show p orbitals on every one of these positions. So I would I'm going to just draw the carbons in on all these atoms. I'll draw the hydrogens in. There's a hydrogen here. There's a hydrogen here. There's a hydrogen here. Hydrogen here. Hydrogen here. And then every carbon has a p orbital on it because every carbon of the diene is sp2 hybridized. So there's a p orbital here, 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 and here. And the way that we think about this molecule from its Lewis structure is we think about there being double bonds between the left two carbons and the right two carbons, with a pair of electrons shared between the left two and a pair shared between the right two. So that is the Lewis structure picture of this molecule. Now, the real behavior of this molecule is there are 4 electrons that are shared in p orbitals, but they're not sort of stuck just on the left side or just on the right side because these p orbitals can overlap in the middle. And so there's overlap in the middle between that carbon and that carbon. And that's what this is, why this is conjugated. So this is a conjugated system because there's 1, 2, 3, 4 carbons in a row with p orbitals that are overlapping. You can think of it as almost like a molecular wire that these 4 electrons can travel through. They're not stuck in any one small little box. They've kind of got this extended environment that they can overlap through, and they can move through the middle of the molecule. So this is a conjugated system. So some of the time the electron density is shared in this space right here. So let's look at conjugated carbonyl and try to understand why that behaves the way that it does now. So here's a conjugated aldehyde, which is very similar to this example I'm showing over here. I think I'm going to draw this up a little higher. And if I draw the molecular orbital picture of this molecule, I'll draw in the atoms. And I'll draw in the hydrogens. And the oxygen has 2 lone pairs that are in sp2 orbitals. And then it has a p orbital that's overlapping with the p orbital on an adjacent carbon, and there's a double bond that we draw, and that's what we think of when we think of a carbon-oxygen double bond of a carbonyl. It's this, and there's 2 electrons that are overlapping in that space. And then over on the right side of the molecule, each one of the carbons has a p orbital, and there's overlap there. And there's a pair of electrons that's shared in that overlapping space by the p orbitals, and that's the carbon-carbon double bond. But what I'm going to tell you now is that it isn't like these are stuck over here and these are stuck over here, because they're close enough that they overlap in the middle, and the electrons can be shared through the system. So what that means is that the electrons kind of ooze into this space between the middle 2 carbons, and they're there some of the time. So what that does to the bonds is it makes this carbon-oxygen double bond a little weaker, and this carbon-carbon bond a little weaker, and this carbon-carbon bond in the middle a little stronger. So the resonance hybrid of this molecule is really kind of like this, where there's some reduced bond order between the oxygen and the carbon, and some increased bond order between the middle two carbons, and some decreased bond order between the right two carbons. So they're more like a bond. They're not quite a bond and a half, but it's definitely not like a complete carbon-carbon double bond, carbon-oxygen double bond anymore. It's lower bond order. Not a full double bond. And because it's not a full double bond, it's not as strong as a full double bond. So it's a little bit weaker bond, it's a little bit looser spring, and it vibrates at a little lower frequency as a result. So its bond frequency, its bond strength has been altered by being conjugated. It's a little weaker, so it's a little less stiff, that spring is, and it vibrates at a lower frequency. So that explains why you're seeing that in the IR spectrum in conjugated carbonyls. All right. Any questions about that so far? All right, let's look at some other examples of conjugated systems, and just so you get some familiarity with how these like conjugation may appear in different places, in different scenarios. When you start knowing what to look for, you'll start seeing conjugation in many, many places. It's really common because it has a stabilizing influence on molecules. So it's a arrangement that molecules like to adopt because it gives them a lower energy state. So lots of things are conjugated in the world of chemistry. Here are some examples of conjugated molecules of other types. Just a brief couple of examples. This is a diene type molecule, and it just happens to have two double bonds. The key is that they're close to each other, so the p orbitals can all overlap. So when you start looking at p orbitals, there's a p orbital, and then a p orbital and a p orbital, and they're all adjacent. So you get this overlap throughout the entire pi system. It's called when I call it a pi system, it's because it's p orbitals that are overlapping to make kind of an extended bonding system. There's 4 electrons in this pi system. There's 2 from that double bond and 2 from that double bond, but they're spread out over the whole system. One really kind of extreme example of conjugation is a benzene ring. So benzene's a molecule we're going to study in a lot of detail in upcoming chapters. For right now, I'm just going to put it up here and talk about it. But if you think about the p orbitals in benzene, every atom in the 6-membered ring is sp2 hybridized, has a p orbital, and those p orbitals are all arranged such that they can overlap. So the upper lobes of the p orbitals can overlap and make an upper donut of electron density, like a circle. And then on the bottom, there's a lower lobe too, and I don't want to be too confusing about how I draw this, but a benzene ring, think of it as like 2 donuts of electron density, and then in the middle are all the atoms. So it's sort of like a sandwich. You got the overlapping p orbitals as your bun, and then or bread, and then in the middle, the carbons and the hydrogens, that's like the meat of the sandwich, or the cheese, or whatever you like to put on your sandwich. So yeah, or a burger, that's another good way, you know, the buns, the electron, whatever. Anyway, extreme conjugation because it's in a perfect circle, and we're going to see that that makes for some really special kinds of behaviors when we hit the next chapter, which is all about something called aromaticity, which is a special type of conjugation that's particularly important. Okay, let's talk about hybridization and geometry and resonance and conjugation. This is another important topic that we will learn some new things about in this chapter. There's a section in the book that talks about hybridization and geometry. So I'll start off with an example here. My example is going to be C, double bond O with an H. And then I'm going to show a carbon with two H's, a lone pair on carbon and a formal minus charge. And then oxygen has two lone pairs. So I'll start off with a question. What do you think the hybridization of all these atoms is? Well, let's count electron groups because that's what you've learned and that's what you know how to do, and that's how you've solved this problem ever since you started learning about hybridization. Oxygen has 1, 2, 3 electron groups. That's sp2. Carbon here has 1, 2, 3 electron groups. That's sp2. If you count this carbon, it's got 1, 2, 3, 4 groups. So you might predict sp3. And up to this point, that would be the prediction. So we're going to talk about, and for right now, I'm just going to put a question mark next to that one because I'm going to come back to that one. It's not quite that simple. Now I want to show you a resonance structure, and here's where the problem is. If you draw a resonance structure for this molecule, and you do this, you could delocalize the electrons, share them differently, and you get an arrangement where the double bond is now between the two carbon atoms instead of the carbon and the oxygen. The oxygen has got 3 lone pairs, and the formal minus charge is on oxygen now. And if you did the predicting of what the geometries would be, hybridizations, you'd predict sp2 over here for this carbon because it's clearly got 1, 2, 3 electron groups. And over here, 1, 2, 3 electron groups sp2. But now you'd look at this one and you'd say, well, 1, 2, 3, 4 electron groups sp3, right? The problem is it can't be both because resonance structures, the atoms don't move. If it were really, they have different geometries. This one's tetrahedral. That one is trignoplanar. This one's trignoplanar. That one would be tetrahedral then. And it can't be both because the molecule can't change geometries when it, between resonance structures because it's the same molecule. So it's got to be one or the other. It can't be both. And it turns out what it is it's not sp3, it's actually sp2. And this one, sp3, it's not sp3, this oxygen, it's actually sp2. And so this is kind of an exception to the hybridization prediction rules that we've discussed. And let me tell you a rule to help you keep it straight. So this is a new wrinkle in your understanding of hybridization and geometry that you're going to have to get used to applying. And there's a pretty easy way to keep track of it, and Smith describes this as XYZ rule. It's pretty catchy, pretty easy to say, and it's a situation that comes up a lot. And here's the gist of it. I'm going to call this the X, Y, Z rule. And the way I've drawn these atoms is intentional. X is a variable atom, double bonded to Y, which is a variable atom, single bonded to a Z atom, which is a variable atom, but the Z has a lone pair on it. Anytime you see this pattern, the Z atom is going to be sp2 hybridized, and that a pair of electrons is going to be in a p orbital. So I'm going to put this into words. In any molecule with an X, Y, Z bonding pattern, comma, the Z atom is sp2 hybridized. And one lone pair is in a p orbital. Maybe what I should say instead of I'm going to say the p orbital of the Z atom. So anytime you encounter this X, Y, Z, X, double bond Y, single bond Z, with the lone pair on the Z, that Z is sp2 and that lone pair is in a p orbital. So let's look at the example we looked at before here and just see if we can apply that. So here's an atom and a molecule that follows the XYZ pattern. X would be oxygen, Y would be carbon, and Z would be this carbon with the lone pair. In this case, that atom is sp2 hybridized and that electron pair is in a p orbital. The reason this works and the reason it wants to be this way is because it gives a low energy state that allows the molecule to be conjugated. If I sketch some molecular orbitals or atomic orbitals or p orbitals on this thing, the lone pair, I'm just going to erase that note. The lone pair being in the p orbital means that it's next to this carbon, which also has a p orbital on it, and the oxygen, which has a p orbital on it, and they're all overlapping. So there's conjugation in this molecule. So it likes to be sp2 because that makes it conjugated, and conjugation decreases its energy. This is the motivation for why molecules adopt a particular hybridization in the first place. It's whatever arrangement gives them the most stable structure. And if it's got that hybridization, it is possible for it to be conjugated, will be conjugated, and that's a low energy state. This one is the same situation here. This is another example of the XYZ rule. Here it's carbon is the X, that carbon is the Y, and the oxygen is the Z. So the two carbons are obviously connected with their p orbitals, but this oxygen has got two p orbitals, or one p orbital. It's got, I'll redraw the p orbital here. It's got a pair of electrons in the p orbital, and then two electron pairs in the two sp2 orbitals. So that lone pair of electrons in the p orbital isn't stuck on the oxygen. It can actually be shared with the two carbons. And so there's this overlapping system of p orbitals that serves as a way to share that pair of electrons with these other atoms. That's the mechanism by which they're shared, is they're able to move through overlapping p orbitals. So this explains the why of how resonance structures work. They delocalize electrons by pushing them through overlapping p orbitals. So, that's the big take-home message here. And just whenever you see a molecule, look for these X, Y, Z type patterns. X double bonded to Y, single bonded to Z with a lone pair. Anytime you see that pattern, that's conjugated in a conjugated system. And so some of the questions in the homework, you're going to be asked to identify conjugation, maybe highlighting atoms that are conjugated. You're going to want to look for adjacent double bonds, like alkene, like double bond, single bond, double bond pattern. That's a clue. That's something you should look at. But whenever you see an atom with a lone pair that's next to a double bond, that's another instance of like conjugation, and it's because of this XYZ scenario. All right, that's a new one. That's an important one to look out for. Question, yeah.
So the atom that shares the p orbital, like the carbon on the first one, that would be the conjugated.
Yeah, so all three of these atoms are conjugated. It's a conjugated system. So conjugation is something that you get whenever you get three or more atoms with p orbitals that are overlapping, and then the conjugation extends through all of the atoms that have the overlapping p orbital. It's not all molecules have conjugation. Some do. Most of the time, it's a portion of the molecule where the conjugation is sitting. It isn't necessarily the whole molecule. But knowing, like being able to look at a big complicated molecule and pick out where are the conjugated segments, that's an important skill, because those are sometimes where a lot of interesting chemistry happens. Okay. The next thing in the chapter is to talk about dienes. So we're going to get started on this. We don't have a ton of time to talk about dienes, but we'll get started with them. And what we're going to start with are a particular class of dienes that are conjugated, because these are going to be really important later on when we look at this reaction called the Diels-Alder reaction. So this is the discussion, the start of a discussion of conjugated dienes. So we're going to take a look at a conjugated diene like this, for example. And there are two different important conjugated conformations for this molecule. It could be like this, and in this scenario, the p orbitals are all overlapping because the molecule is planar. Then you could rotate about this carbon-carbon single bond in the middle. And when you do that, when you rotate it, you're going to break the conjugation because the p orbitals can't overlap when you turn until you reach another planar conformation. So there is going to be another conformation of this molecule that looks like this. So these are two conjugated conformations of the same molecule. And they have different names. All the other conformations are not conjugated because the p orbitals can't overlap when they're not parallel to each other. So, but these are two conjugated versions. So these are particularly stable conformations of the molecule, and they have two different names. So the way to distinguish these is to imagine drawing a line down the central single bond of each of these. And if the alkenes are on opposite sides, this is a conformation called s-trans. The S is for single bond. So what it's talking about is not cis and trans in the traditional sense with respect to the stereochemistry about an alkene, a carbon-carbon double bond. It's talking about what's going on at the single bond, so S-trans, that the alkene pieces are on opposite sides of this line. This one is called s-cis conformation, because the two alkenes are on the same side of that line that the single bond is defining. And they don't have the same stability because if you think about like what's going on with these, there's an H here, and there's an H here, and there's an H here, and there's an H here. And these two H's are kind of getting in each other's space a little bit. So that one's got a little bit more steric strain associated with it. This one over here on the other side, it puts those groups much further apart. So this one is more stable. This one is less stable. Less stable. This one is more stable. So it can adopt both conformations, but you'll notice I made the arrows different sizes. It prefers the S-trans over the S-cis because the S-trans has less strain. We're going to see when we look at these, when we look at this situation and we start changing H's for things that are bulkier, the steric strain problem changes. It can become a lot worse depending on where the methyl groups are, and that influences how much of the time the molecule wants to spend in this S-cis conformation. So we're going to talk about that on Friday. So have a good day, and I'll see you then.